All right. So finding volumes of solids doesn't always have to be a washer or a disc. It can be any shape we want it to be. So if I say that we want a rectangle, and I want the rectangle to be W by L, but I want the length to be twice the width. Does that look about twice as, does the L look about 2W in that picture? And let's say then that I want to use a root function as the sides. Can you picture a root function? So if I'm going to map this out, and again, we'll try to keep it simple. We're going to use parent functions right now. So I'm going to use the parent function of square root of x. All right? What's some nice numbers to go to? Well, any perfect square. Do you guys agree? So let's start at 0, and let's go to 9. All right? Because 9's got a nice number. All right? It's 3. And I want the rectangles to have a length and a width when I cut the butter knife. Does that make sense to everybody? The length is the vertical distance. The width is going into the board. All right? And I want to know the volume of that solid. All right? Again, anytime we start with volumes, anytime, it always starts the same. And we're doing it with respect to the x-axis. And think about this, guys. Our butter knife cut is perpendicular to the x-axis. If I take a butter knife cut perpendicular to the y, it's going to have to be dy. Our butter knife cut, our cross-sectional areas are to the x-axis. So it's dx dx, ax dx. And I'm going to say, oh, okay, so when I do a of x, that's my shape. It has a width, it has a length, and I got told that the length is 2 times the width. So when I go back over here, there's some stuff I can automatically do. I know it starts at 0, goes to 9. And everybody, I don't get cute. You guys all agree it's exactly length times width. That's what we start with. Not a disc, not a washer. It's a rectangle, so it has to be length times width. And then what I say is, oh, okay, let's see here. I said this is the length, but if this is L, going from the x-axis to the hair, you guys all agree that L is also equivalent to y this time? But what is y? This time y is the square root of x. All right, well, down here, I would be more tempted to say, well, also then we know the width is the length divided by 2. So if L is square root of x, guess what this is? Square root of x divided by 2. All right, I come back to my function, 0, 9, square root of x times square root of x over 2 dx. Again, we don't try to integrate products, do we? We make the product, square root of x times square root is x over 2. And this is where I like my limit laws, all right? Because I would actually think to myself, well, it's x over 2, but can't I do that? Yes, I can. And that gets my math a little easier. So I have 1/2 times the antiderivative of x is x squared over 2. Why don't I need plus c? Because it's a definite integral, right? I'm evaluating it. I don't need to put plus c. Has numbers. I want the area. So I take half of 9 squared over 2 minus 0 squared over 2. 81 halves, you guys agree? Times a half. The volume of that figure is 81 fourths. And everybody, this is really tough for us right now. I didn't revolve it as a circle. I didn't revolve it as a circle. I kept it as a rectangle, all right? And it changes the formula a lot, doesn't it? Think about it. If we were revolving this as a circle, if we had a of x, again, all the legwork down here. You know, this is all the evaluation to get 81 fourths. If I group that and make it real small, all right? If I said, if you wanted to do this as a circle, you could. First of all, hopefully everybody sees it as, if you were to revolve that around as a circle, it's going to be a disc. There is no center hole, is there? And what happens is our whole formula changes. The units might not change, okay? But we get a whole different problem here, because then you say, oh, this is the, instead of being the height of the length of a rectangle, right, it is now the radius of a circle, all right? And that can be the square root of x long, right, because it's y high. Well, obviously that's going to change your answer quite a bit. It's going to have pi in it. It's going to be a whole different value. Everybody, I can do anything I want. I can call it any shape I want. I can define this distance as anything I want. I don't have to make that the radius. I can call it the diameter. When I start doing stuff like that, that gets extremely tough, all right? But we're going to start by just doing some simple shapes and keep integrating. But every time we do this, my expectation for you guys, unless you're super good at it, I mean, I'll always go down here and look for 81/4. All right, that's where I start grading. If you have 81/4, awesome, you're done. But the next place I go, all right, if you don't have 81/4 for partial credit, is I come back and see, do you have the right cross-sectional shape? And then I go to your graph, all right? As crazy as that sounds, identifying this shape is what makes the difference in whether you can find volumes of solids, all right? How do you know what it's going to look like? A glob of practice, all right? How do you know it's going to come out to look like this, you mean? That is a lot of work, and I'll never make you sketch that. I will never make you sketch that, okay? That just takes a lot of practice. And just to get good at finding the volume is a big step. I'll leave that for your solids classes if you're going to become a math major, okay? Can't do it all in high school.